All right. So one of my favorite quotes of all time comes from a very difficult programming challenge that someone posted in 2013. And it turned out to be of unprecedented difficulty, and 6 people teamed up for 1.5 years to solve it. And they led their response with what began as a quest and became an odyssey. And I quite like that comment because I think that it kind of inspires me to look for quests that would become odysseys, to try and challenge myself and do things that are outside my comfort zone and try and go for something really difficult. And so this is something where I went for something where I had no idea how it was going to go. I thought it would actually go well, and then it didn't, but it actually went quite well. But let's go ahead and get started. So my project is SAMDi, or SAMDi if you don't like people named Sam, and it stands for Simeon's Awesome Math Diagramming. And the idea is that there are a lot of diagrams in math, and we want those diagrams to look good, and typically they're not the easiest to make. There are a few software out there that actually help and do this, like Asymptote and TickZ. And these are, the problem with them is that they're very difficult to use. They're language-based, so you kind of have to know how to code in order to actually start using them. And then, while they are very professional looking, they're just very difficult to use. There's a few that actually work with drawing by hand, and they're also quite difficult to use just because it's very hard to read hand drawing and turn it into a diagram. So there's not really many existing projects that I actually like to use. And the reason that I'm looking for these at all is because I'm a math teacher with dysgraphia. I like teaching math to people. I really enjoy math. I like working with it. However, I have dysgraphia, which is a writing disability, and that makes it very difficult to draw diagrams just by hand. So I want software that helps me do it, and there's not really much out there that really works with me. So I wanted to make that. And here's an example of what TickZ in particular looks like. You can see all this code kind of in the background on the left and the diagram on the right. And you kind of get the sense that even drawing simple things gets very complicated, and why I wanted to do something new. And with that, I'm going to go ahead and begin with the demo and not skip to the tech. So this is just a minimum viable product written in Python, and the idea is you run it and you get this little thing. And I'll go ahead and scale that up a little. And then there's a lot of options for shapes on the left, and there's also shapes on the right. So you have triangles, circles, rectangles, all the typical stuff. There's a color picker here, which looks really nice. You can change the opacity of these shapes. You can also add labels like A, B. The difficult thing here is actually moving things around and connecting them to things. So I can take this label B and connect it to a circle, or I could take this label A, connect it to the tip of this triangle and move that around. And that's really fun. There's also a snap to grid option, and then generally there's dotted lines, there's line thickness. I can make a thicker line, for instance, with this, and it's a little trickier to see, but if I scale up this triangle, then it looks a lot larger. And that is essentially the core of the project. And since the focus of this is actually to teach mathematics, I'm going to go ahead and do a very brief mathematics lecture. So the starting character of our story is that we have a circle, and we essentially place a triangle within the circle. And I'm going to go ahead and move everything here. And the idea is that you actually want to place this triangle along the diameter of the circle, and then you want to move this tip somewhere along the circle. And an interesting thing about this is that everywhere you put this tip of the triangle, as long as it's touching the corner, it's going to be a right triangle. That angle is going to be a right angle. And it might be a little confusing as to why this is true to begin with, because it definitely doesn't seem obvious. You would expect the angle to change as it moves around. But it turns out, if we just take this triangle and we make a copy of it and flip it around, we end up getting a rectangle. And that's a very simple visual proof of why this fact is true. Why, if you do have a triangle within a semicircle like that, then you are going to get a right triangle, because you have 2 diameters and that makes a rectangle. And that's going to suffice for the demo, I think. And returning over here, the main tech stack here, I use Python as the main language. Kiwi in the middle is the graphics framework, and I use NumPy for some extra numeric stuff like calculating angles and doing a lot of linear algebra, which turns out to be necessary for a lot of rendering and scaling and shifting and all of that. And now that I've kind of introduced the project and what it was built in and kind of the moving parts of it, I want to get started on the Odyssey, or the journey that I went through to get to this point, because it turns out to be a very long journey. So I started this, first few weeks of the project. I was working mostly on just adding new shapes and getting the main layout out. So I made this layout, I started adding shapes. I was struggling with graphics from the beginning, and I started to put a lot more work into this thing called tethering, which grew to be a very complicated problem. And tethering is this idea where you have shapes and you link them together, and you want to be able to move shapes such that if you have some constraint and like two lines are parallel, for instance, if you move one of the lines, you want the other line to also move to remain parallel. I said parallel, it's perpendicular. It also works with parallel. If you have one line moving, then you want to make sure they're both parallel. And the problem with this is that it's a very difficult problem. It turns out that you can't just have it so you're moving a triangle anymore. You have to have it so that you check all these constraints. And if you reach a contradiction, what do you do? And there's so many edge cases to handle. And it just kept growing, and I kept running into this problem, and it confused me for a while. And I was communicating with Mr. Comier in the weekly meetings that this is a barrier that I was having and that I was putting a lot of time into trying to solve it. And I pretty much kept working on it. Eventually, I found this field called dynamic geometry, which turns out to solve very similar problems to this. Dynamic geometry is a mathematical field which focuses on drawing things on computers and seeing what happens when you change those items. And so this is something called a geometric straight line program, which shows how to construct an image programmatically and very easily find contradictions in an image as they arise, which is one of the big issues I was encountering. And it turns out to be quite complicated to write this. And so just to give an example of something in dynamic geometry, this is something I made with Desmos earlier. And the idea is that you have a constraint on these three circles, which are all fixed to a center, and then they have their circumference lying on this point. And you want to be able to move the point around and have all these circles update to match that. And just implementing that without doing it programmatically turns out to be very difficult. And so that's what kept making the project kind of grow exponentially in scale. And eventually I found a certain research paper called About Tracing Problems in Dynamic Geometry, which introduced me to this whole field. And it's such a fascinating field. It's such a fascinating problem. And there's so many interesting things in here. And a lot of people have looked into it. On here, you can actually see an example of a much more complicated version of what I was trying to do, where you have a bunch of constraints. And this time you have loops and circles and tangential arcs. And things get really interesting. And you also have a lot of constraints. And so I spent a lot of time on this, and generally the focus of this project is I wanted to put a lot of time into figuring this out because I thought it was really interesting. When I contacted Comier about finding the research projects on this topic, I was like, so I don't think I'm going to actually be able to meet this requirement, but I do want to actually focus on the requirement because it's really interesting. And also, can I mention half the research papers are in German, so I had to translate most of them using Google Translate. That was really fun. And so ultimately, it's this complicated project, and now I want to get into how I actually solved it. And ultimately, the emphasis I want to have here is that while the product I showed earlier is pretty simple, I put a lot of effort into making it scalable. I wanted to make adding shapes as easy as possible and adding functionality as easy as possible so that even if it's not the best now, it can be scaled on really easily. And so I'm going to be focusing on the architecture for a while to talk about how I made sure that adding shapes is as simple as possible. So first of all, the main power triangle here of shapes and points. So the idea is that on the screen you have a shape store, and this stores shapes and points, both of them. And the shapes also store a list of points. And one thing that happens internally is that the points in the shape store are actually the same points in a shape. And so you're kind of making a redundant copy of all of these. And the reason for that is it allows you to easily search for points. So if you're checking for mouse collisions or just generally shaped collisions, you can use some more efficient algorithms than just checking every shape and checking every point of that shape and running all these different types of collision tests. And you can use something called a KD tree, which is a bit like a binary search, but in multiple dimensions. That's also really fun. I really loved working on this project. It's so cool. Next thing is the shape, and this is kind of the core of everything, because if you want to do geometry software, you want to be able to draw a lot of shapes. And the way I architected the shape, the really important thing is actually these three methods right under the line: draw, collides, and update. And in fact, to add a shape to this software, you have to add a button to it because the UI doesn't quite automatically query for things. But also, all you have to do for the shape is you just have to tell it how to draw the shape. Like if it's a rectangle, you have to tell it how to draw a rectangle. How to detect a collision with the shape, and then how to update the shape. So if you're moving a corner of a rectangle, if you imagine you have these 4 points and you move one of them, then you're actually moving the other 2 points that are next to it because it needs to stay a rectangle and not just become a rectangle with 1 point slanted off to the side. And the great thing about this architecture that took me quite a while to work out is that we have just having to add those things, and there's also some other minor implementation things like you have to name the shape. But for the most part, all you have to do is just drawing collision and updating, and that's the only hard part about it. A lot of this is actually given by a superclass as well, so you don't have to worry about it at all. Getting away from the like UML diagrams for a minute, just focusing on what it actually represents. So the idea is that a shape is made up of points, and you have, for instance, a triangle has 3 points, a circle can have 2 points, one in the center and one in the circumference. And then linking things up is done by figuring out which points are connected, moving one point around, and then moving another point around with it. So if you were to grab this purple point in this diagram and move it around, the update method makes sure that the blue point on the circle would also move with it. And then the drawing method would make sure both the shapes are redrawn. And that's essentially how that part works. And then for more dynamic geometry, there's a lot of different types of constraints that need to be covered. And this is kind of a simple list of what those constraints typically look like. Some of them are a lot easier to implement than others. A lot of them just boil down to relatively straightforward math problems that you can be solved programmatically. And then now we move on to retrospection, now that I got all of that done. So what went well? Super fun to work on. I know I used a lot of complicated words, but people who know me know that I just love working on complicated problems, and I really got to challenge myself all over the place. Like I remember when I first found the like research papers on this topic, I was like, oh, other people are studying this. Oh, that guy has a PhD. Oh, I am so going to enjoy working on this. Another thing is that implementing things once you work out all the logic turned out to be really simple. Graphics were a huge challenge for me because I'd never really done like non-web software that had graphics and like did a lot of it. And it was a big challenge, but it turned out to go quite well once I got over that challenge. Tethering went pretty poorly. That was the whole problem I was trying to solve that ended up growing dramatically in scale. And while I did make considerable progress on it, and I did do a lot of research on it, it ended up in a situation where there was just too much that I had to do to set that up right in too little time. And I kept working on it for like 4 weeks. And then eventually a week ago, I just told Kumar, all right, this is not going to be done in time, but I have put all this work into it and I can still talk about what the journey was and how exactly this worked. Another thing was sunk cost. The whole reason I got kind of into this situation at all was because like 6 weeks ago, I got into tethering, and then it turned out to be more difficult than I thought, and then I kept working on it. And then this sunk cost fallacy kicked, and I said, okay, I've already put so much time into it, I have to work more on it. And then that kept scaling up until the last week, and I was like, oh, this doesn't work. Now I've wasted something like 7 weeks. Well, I've also worked on other things in the middle of those weeks. I did take breaks from the one big problem to work on other things. So it wasn't a complete loss, but a lot of time on this project was on this very interesting problem that I didn't end up actually solving completely in the end, though I did make considerable progress on it. And the other one is just overworking. I worked way too hard on this, and I have a bit of a perfectionism issue, and everything was broken, and I was like, I have to work harder, and that ended up being a big problem later on. Finally, challenges. I learned so much dynamic geometry. It's so great. I like it. Another one was the input method. I haven't actually talked about this a lot, but I've only really done console input and like web input before. So just having the user press a key and it would like copy the triangle, that's something that's interesting to work out for the first time. But I think once you find the one kind of method that most people use for handling inputs, it kind of becomes standard. And then the architecture was a huge challenge, and it looks simple in hindsight, but reaching that point involved a lot of dead ends and such. And so that was a big challenge that I think I ended up solving pretty nicely. And I think all that's left is what I learned. Hey, more dynamic geometry. I keep putting that in there, and then it keeps coming up because I like it. Architecture. Oh, hey, I also mentioned that one. I learned how to, oh yeah, one thing about architecture is that one thing I wish I took before this class was design patterns, because design patterns turned out to help me way later on in the class, like way later on this project, because it turned out a lot of these things, like for instance, shapes can be represented with the command pattern, and they have states and they have commands that can be invoked on them. And nobody really taught me about design patterns until after this class started. So I had to go like, okay, this helps so much, I have to refactor. So I went back and refactored everything, and that was pretty helpful in hindsight. So learning that and applying it was really great. Architecture, I got just better at it overall. That's kind of what I mean by that. Dealing with roadblocks, this is like a big roadblock where I don't think I've ever really had a problem where I would just keep trying to go at it and it just keeps failing. Like I would fail like once or twice and then figure it out on the third try or something like that. But this is the first one where I just kept going at it and then it didn't work out in the end. And I think I learned a lot better about dealing with that, and I got better at communicating because of that roadblock. And I also got a lot better at respecting planning, because this roadblock is rewriting all the plans and things are working around. But because I had a plan, things kept feeling good and it kept allowing progress to happen even when I was getting distracted internally by this one big thing. And finally, what I would do differently, that's a bit of a tricky question because the thing about this problem is that I don't think I could have really recognized that it was difficult early on because it kept feeling simple and it kept feeling simple. And then I found the papers and I was like, okay, this is complicated, but it still felt simple. And I think just recognizing that it was a difficult problem earlier on would have probably helped. But it's still a tricky question because I did really enjoy the project. And even if it doesn't look especially great, I did love working on this and I made great progress, I think, and I'm proud of what I did. One thing I would do is probably a different input approach. I tried to do like drawing software because I wanted to use a pen. And one thing that hit me kind of later on in the project is that the language tools aren't actually that bad. And I think I could do a language-based tool. They're just like complicated because they do a lot. But if you simplify them a lot, and I think I do have what it takes to simplify it. For instance, on the right here, we have something from SAMDi's geometry module, which is another Python library. And you can see that it looks a lot simpler than the code I showed earlier that had all this, the curly braces, and it does something similar to what that diagram did. And I think that if I went for something like that and focused more on usability and made it accessible to non-programmers, it would have turned out better than what I did now. And finally, disregard perfectionism. Your project's not going to be perfect. I wanted it to be perfect, and then it wasn't. And I think that is all for Rachel. Yes.
You did very good. Not many projects out there that could lead to academic research papers.
Especially in German.
Yes. Yeah. At any point during this project, did you yell "power up"?
I can't say. Oh yeah, I have not really taken a Kohler math class because I tested out of all of them, so I don't really get those references. Yeah. I'm sorry. It was prompted. I try to be humble. All right.
Did you mention the technology used for the app?
For the app? Oh yeah, that was Kiwi, which is the graphics library in Python. And the reason I chose Kiwi was because I looked into a few of them. There's also one like tkinter, there's one called Piglet. And generally I liked this one because it focused a lot on usability. And I also did a lot of like demoing before the Capstone quarter even started to just see which one I liked most. And I liked Kiwi the most.
Okay.
When you were drawing the triangle inside the circle, did the edges snap to the circle, or
that was mostly me being good with the mouse. At one point I did have it snap to the circle, but that led to enough bugs that I removed that and I never got around to adding it back because it gets complicated again. But
right click it and say snap.
yeah, the problem is that the way circles are implemented makes that kind of difficult. And that's one of the interactions that actually was in there. It's having something be connected, and it's just one of the interactions I didn't get to.
And then you mentioned that you built this based on the fact that it's hard for you to draw graphs.
Yeah.
Deeper, I'm assuming.
Yeah.
So is there potentially a future upgrade where you can type a formula in and automatically generate the graph and allow you to manipulate it?
I was looking into that, and I think possibly I will do something like that in the future, but that's one where there are good tools for it. Like Desmos will handle, if you give it a formula and it gives you the graph back. And I want to focus specifically on non-formulaic geometry because like just having a formula for a circle is really easy and there are countless tools that do that. But just drawing a circle and having these things like triangle relationships and tangential lines, that is a lot less easy to do with equations, and not as many tools do that.
Yeah, I think it's really cool. And then another cool feature I think is be able to print the graph out.
Ooh, I didn't actually demo that, but you can actually save the graph. There's actually both saving in the application, so you can load it again. It preserves all the connections, and there's also image saving. If you'd like, I can show that now.
Yeah,
okay. Okay. Oh, sure. I'll show it now, and then, yeah. If I run this again, I'll just put some shapes on things. The saving is a little janky at the moment, but we can see that it's saved to these files, and then it's going to show up in output over here. And then the image we just made is in here. And I think I have to reveal, oh, there it is. Yeah, that shows up. And so it is saved. And then the other one is the JSON file, and that lives over here. So now this preserves all the information you need to reconstruct that same diagram from scratch. So if I went and loaded this, then it would show the same diagram.
Is there a theme setting? Like, what if I want to highlight that one?
I considered doing that. It's going to be easy to do. It's just pretty much a button toggle, but it just wasn't something that really occurred to me. It's like a 10-minute change. I know exactly where it lives. In fact, I can just show you right now. Right here is where you set the Windows background, and then there's also one for the canvas background somewhere else in there. And you would just have a toggle that sets this clear color here and also sets the canvas color.
And then the last one, how secure?
How secure is it? Hitting me with my own medicine. That's actually a decent question. I did anticipate this one because I expected someone would ask me. I mean, you have to ask, what are the attack vectors here? It's not connected to the internet or anything. You're saving diagrams internally. It's not doing any telemetry whatsoever. So the security is entirely on you as a user to not post a confidential diagram that you did of a nuclear project with the US government on the internet. You can encrypt these images if you would like. They're regular files. You can use any encryption algorithm. But it is secure because it's not connected to the internet, and you can't get more secure than not being connected to the internet. Yes.
So dysgraphia is a new term to me. I thought that was so cool that you were able to take, you have this passion for math, but even though you have this hindrance, you were able to find a solution for that. So I'm just wondering on a personal level, like how did you figure out that you had dysgraphia? And have you done any research on other people who might also have this and would really benefit from what you created?
Well, yeah, part of it is that I have kind of a minor case of dysgraphia. Like generally it's just, I found out because I had problems like writing and drawing for pretty much my entire childhood. And eventually a doctor said, oh, by the way, that's a thing. And then there are people who have it much worse than I do. And so I wanted to make it mostly for them because I kind of can draw now after a lot of practice, but there are some people who really struggle a lot more than I do. And I wanted to do it for their sake. And then I think I have been working to try and make it so I could share it with them. I don't think it's quite in a state where I'm content to just give it away yet because there are still some things that I think could be much better. But generally, yes, I did intend to make it usable and also make it available to people like me.
Very good.
Are you going to continue the project?
I think I'm not going to continue this specific iteration because there are some things like technical debt that I really want to just refactor, and I think I'm going to restart at some point. But I still think that the whole problem domain is really fascinating, and I think that I still want to do something like this, even if this specific iteration doesn't work out. I'm going to be probably restarting and doing it again at some point.
All right, thank you.